So the task that I'm concerned with is query by example audio retrieval, in which, as many of you know, you can use for searching sound effects libraries, interactive computer music performance, and my personal motivation, programming complex audio synthesizers. So query by example audio retrieval task is when you give an example audio object to a system and returns similar audio objects. However, while machine measures of audio similarity are good to a first approximation, machine audio similarity measures of very similar objects are noisy. So one observation is that humans perceive some time regions of audio as more important or as salient than others. For example, in Thayer's 1974 experiment, in which there were played audio clips and had to choose whether it was a trumpet, flute, oboe, or clarinet. When the attack of the trumpet was removed, the number of correct identifications dropped from 82.9% to 46.1%. This shows that much of the information of the trumpet resides in the beginning of the audio note. So for example, imagine a trumpet that is playing a very long tone. If, according to many common audio similarity measures that build up distributions of audio features, the important regions near the onset would get diluted, and the representation would lose its distinctive characteristics. So in general, if we want to treat all moments in time, in audio as equal, important aspects of the audio may get diluted. So our idea is to incorporate perceptual salience of different time regions into machine measures of audio similarity. These similarity measures would then more closely match human measures of audio similarity and therefore improve audio search results. So we are calling the importance of human listener places attaches to a particular time segment of audio in relation to its surrounding time segments as temporal salience of audio. This is what we like to estimate and incorporate into audio similarity measures. And as far as I know, in audio there's not any accepted models for temporal salience. However, there do seem to be at least 3 known cues for temporal salience in audio that have been reported over the years. I mean, one is loudness, of course, which is obvious. Something is quiet, place special importance on it. Another is proximity to onset. This cue is related to the attack of a sounded note. And while the definition of attack varies amongst researchers, one thing that they do seem to agree on is a region near the region of audio near the beginning of the note, which is important. And so I'll refer to this as proximity to onset. And a third one is expectation violation. And this is exactly what it sounds like. It occurs when a pattern has been established, results in certain expectations, and when that expectation is broken unexpectedly. Here is an example in which the RMS level of the sound is equal throughout the audio clip. So in that case, neither loudness nor proximity to onset would correctly weight the area that captured our attention, which was further in the sound. So therefore, we need to consider expectation violation if we want to approximate temporal salience. Expectation violation is shown to be a cue for temporal salience in audio object sequences. However, it has not necessarily been shown to be a cue within audio objects. In this work, we are focusing on expectation violation within an audio object. We want to approximate expectation violation and therefore have a cue for temporal salience. That is the goal of what we want to do. One assumption we are going to make in doing so is that expectation violation is correlated to change or novelty. As I said before, they're not the same, but they often, in many cases, they do co-occur. So the questions we would like to answer is, does novelty within an audio object draw listeners' focus? Can we estimate novelty with machine measures? And can we use novelty to improve machine audio similarity measures? So the two measures of novelty that we'll be using both capture short-term local change in spectral properties. The first is Foote's novelty measure, which is a well-known existing method. And the second is what we call power spectral density novelty, which is a method that we devised. And Foote's method peaks at transitions from regions of self-similarity to dissimilar regions of self-similarity. And power spectral density novelty compares spectral densities built from roughly 100 milliseconds before and 100 milliseconds after the measurement point. We presented subjects a series of trials. In each of those trials, we presented a reference audio clip and 2 modified copies of the audio clip. One in which the half-second window in the highest novelty region was time compressed by a factor of 4, and one where the half-second window of lowest novelty region was time compressed by a factor of 4. And then we asked the subjects to rate similarity of each clip in relation to the reference. So here's an example. Here's a reference clip. And then, so if we analyzed it with using foot novelty, we get that curve on the right here. And so if we try to find the window with the lowest novelty, lowest half-second window with lowest novelty is this green region here, and the region with the highest novelty is this red region here. So then if we take a copy of the reference clip and modify the region of low novelty and time compressed by a factor of 4, we get this. And then if we modify the region with high novelty by time compressing by a factor of 4, we get this. Oops. So we used time compression instead of a spectral modification because we wanted we wanted to minimize the effect that we had on the novelty curve after it was modified. We didn't want the low novelty region to turn into a high novelty region and affect our results. As I mentioned before, there's 2 other cues that we know of that would be cues for temporal salience. One is loudness and one is proximity to onset. So to come to control for those other salience cues, so we highly compressed the dynamic range of all the clips to account for loudness, and then we also included reversed copies of all the clips to account for the attack or the proximity to onset. The subject population was solicited through personal contacts, flyers, and mailing list. We had 19 subjects, and one key thing was we wanted all of the subjects to have musical experience, and so we pre-screened for this, and there was a mean of 11.25 years of musical experience across the subjects. Many subjects were still simply not consistent with their continuous similarity ratings, and some trials were also inconsistent across subjects, so in general, a lot of subjects found certain trials difficult. So we examined our results on both the full set and kind of a consistent set of subjects and a consistent set of trials. Because of the difficulty in allowing users to provide continuous ratings of similarity, we evaluated this relationship on a kind of forced choice agreement. In other words, we say that a subject is in agreement with the novelty measure when the clip that they chose as more similar to the reference was the clip whose novelty integral was less than the high novelty, whose low novelty integral was less than the high novelty integral. So while we use the foot novelty measure to define what the region of high novelty and low novelty was, we also evaluated the audio clips using those regions with the power spectral density novelty as well. So that's how we use both without doubling the number of trials. The question we'd really like to know is, can we use novelty to improve machine audio similarity measures to improve distance measures? So novelty differences alone are not sufficient for general audio similarity, despite the previous slides. Remember, those were done on very similar audio clips. However, we can easily incorporate this idea of novelty and temporal salience into existing audio similarity measures. So we did this in 2 different ways. One way was incorporated to a bag of frames audio similarity measure. So this one was simply a similarity measure that just used 13 MOCCs for each audio clip, represented by a mixture of Gaussians, which were compared with symmetric KL divergences. And we incorporated novelty into that by weighting the distribution of the features by novelty. So regions that had high novelty were weighted more highly than regions with low novelty. And we also tried a dynamic time warping audio similarity measure in which we morphing on Euclidean distance also using 13 OCCs and incorporating novelty in this measure by using it as the warping cost in dynamic time warping. The baseline measure is the blue one on the left of each of these plots. That does not incorporate novelty, so it's the same similar measure but without the weighting or without using the novelty as the warping cost. And we can see in both for the back frame and the dynamic time warping cases that when we incorporate these novelty measures that we do get a improvement over the baseline. Our goal was to estimate temporal salience in audio to improve audio similarity measures of very similar audio objects. We proposed 2 novelty measures to approximate expectation violation within audio objects. And we designed a study in which subjects were asked to rate the similarity of very similar audio clips, and we showed that the novelty measures were moderately related to temporal salience, and we showed that we can actually improve audio similarity by incorporating these estimates of temporal salience.